All right, folks, welcome to day 3 of our training week. We'll kick things off with Daniel Schulte talking about RF cavities today.
Okay, so since the time is limited, I try not to do any calculation on the blackboard, even in the questions maybe we can do. I thought RF should be included in the school, and I'm not an RF expert. I deal with RF experts in my role as leading the different designs. Just if you look at the overall layout of the muon collider, you have plenty of RF. You have normal conducting RF at the beginning of the H- LINAC. You have superconducting RF for most of the LINAC. You have normal conducting RF in the accumulator and compressor ring, in the capture, then in the cooling system, and then you go to, again, superconducting RF here in the accelerating part. And you have a very little bit of RF in the collider ring. There was a question about that. You lose like 10 to minus 4 of the muon energy. So you have like a cavity or so in the collider ring, but it's a single one, roughly of that size. There are two types. There is a normal conducting. As I will show, this is more robust in different ways. And the superconducting is less robust, but more power efficient and also reduces the cost. So that's why at the beginning, you lose protons. So you want something robust, and you stop losing them so you can go to superconducting. Here you use gymnastics in a short moment also. So this is good. Here you lose particles. Here it's not so much that you lose particles, but that you operate in a magnetic field. And then again, you go to superconducting because of that. Okay, so that's the logic. Now, what I will show you is based on mainly considerations on main Linux, because they use more RF than anybody else. They're driven by RF. And then for us, it's actually more complicated, but it's already complicated enough, maybe like this. So bear with me for a moment. So RF is a key cost driver. And there is an important part of the cost, actually, that doesn't come from the cavities themselves, but from the peak RF power that you need to put in. Normally, the cost for a klystron that provides RF power depends on the peak power, at least as much more, actually, than on the average power. So reducing the peak power is a standard thing. And then it's also one of the main power consumers. There are different types of cavities, and just to group them simply, there are superconducting ones and normal conducting ones. Why one is written with a hyphen and the other isn't, I don't know. Somebody may explain that. That's the way it is. And you have different designs. Standing wave, which is associated with superconducting cavities all the time, but could also be used for normal conducting. And traveling wave, which I will just show for pleasure. We don't use that in the muon collider, but like a linear collider based on normal conducting RF would use that. And then there you have different choices in addition. Okay, so why cost driver? This here is the cost of the RF on the muon collider at 3.2 TeV, and this is the one at 7.6 TeV. So you see, 1/3 is roughly comparable to the magnets here. And here, the magnets take roughly half of the overall cost. And then it's the RF, and then all the rest is less than the RF. All the rest together is less than RF. So it is critical, and that's why it needs to be discussed. And it's, again, the two technologies, magnets and RF. You saw that with the equation, electric and magnetic fields. Okay, now let's look at an IRC cavity, which actually happens to be the one that we believe we can use in the RCS, even. Okay, that was a pleasant surprise. So this here is a 9-cell cavity. You can count that. It's roughly 1 meter long. The effective length is actually 1 meter and 3.6 centimeters. It has a gradient, operating gradient of 31.5 megavolts per meter. It's superconducting, standing wave. Come back to that. And it has a constant impedance, which is always there. So this is what we believe we can do. Now, in a LINAC, but also in any other system, you have actually your RF here, and you power it with klystrons. And then in a LINAC, you have some lattice, which consists of quadrupoles to make sure that the beam goes straight, and some instrumentation. In our case, we in addition have around that dipoles to guide the beam. Okay, so that's how the system looks like. And what you do is you get the power from the klystron, and then you split it into the different cavities. Here you see like a cryostat that contains the cavities, and so it's a pretty big fat object. Now, standing wave, what does that mean? It means that you have the cavity here, and more or less it's like reflecting the fundamentals on this side. Sorry for the graphics, it's limited. I do this with TCL because I'm really bad with any of these graphics tools. So you have the power from the klystron, you put it through a coupler into your cavity, where it bounces back and forth, so it's trapped. A little bit is leaking out here again, which in a circulator you have to send to a load. Okay, so this means that you have a long time to fill the cavity because you sort of constrain the flow out of, from the energy in the cavity out here with your coupler. I come back to that. If you had a traveling wave cavity, that would be different. I'll show that in a moment. Okay. Simple put, you have the RF in there, and it's like oscillating an amplitude, and it's a wave going forward, a wave going backward, which makes a standing wave, and so it looks like that for a lay person like me. Send in a particle, and you do that in the way that it always sees an accelerating voltage. Trivial. And actually, if you were to send another particle at 180 degrees apart, that particle always would be decelerated and would actually put energy into the cavity. So that can happen. If you draw this now as a function of time, at the moment when you enter the cavity, you have a sign like energy gain in the cavity if you do the integral. And one thing that is important, the one wave, the forward-going wave, actually is the one that drives the particle. The backward-going wave, on average, doesn't have any impact on the particle. It has local one, but then it's compensated later on. So the energy you have in there compared to a traveling wave where we go together with the beam is a factor 2 larger because there's half of the energy that's useless. Well, it has some use because it keeps in the cavity. So these are field lines in the cavity. This is a normal conducting cavity for the muon cooling system, and you see the lines here. And actually what you, this here is the field level, and what you see is that the field inside of the cavity, in the center of the cavity, doesn't depend very much on the transverse position. That's how you design the cavity, and that's, so you have, for us it's good enough, you think there is a hole, and within that hole the acceleration is always the same. The transverse position doesn't matter. It matters if you come close to the surface and if you have things that are not circularly symmetric, but that we don't, okay? So that's how it goes, and you see you have field lines also here. So there is energy in these volumes, but you really have, I mean, you try to concentrate the energy of the cavity there. What limits a superconducting cavity? There are different things. There's breakdown that I will come back to for the normal conducting ones. But the feature of the superconducting cavity is that the Q is very high. So that means that you have very little losses inside of the walls. And these Q, that's, I have the formula later for that, depends actually on the voltage in the cavity. And the voltage in the cavity means also that you have electric and magnetic fields inside of the cavity walls, or next to it. No electric field inside the cavity walls if it's perfectly conducting, but close to there. And now if you increase the field, then the superconductor has a harder time. That's one thing. So there is a fundamental limit of how far you can push it. If the magnetic field becomes too high in the cavity walls, then it breaks down in the superconductivity. But in practice, you see that actually the Q degrades with the field at some point. And that's the black magic. That's roughly around here, 35 megavolts per meter. So this is the gain, the goal for the IC. This is an older plot. And so there's some black magic how to make the cavity give you a high Q up to the highest possible value. And then at some point it will break down fundamentally. But this limit here where sort of the Q becomes smaller happens actually way before the real gradient theoretically you could attain would be here. Now, and also all these cavities are not the same. So you have a spread. You have a set of cavities and they have an RMS 10% or so different gradient that you can get out. And what you do in practice then is you throw away all the cavities below a certain level. So this here is an old IC plot. This is the goal, 35 because you need a bit of reserve for operation. So it means 31.5 in practice, 10% left. And so all the cavities below this value are thrown away. Above this value, you cannot power them more, but you can still use the cavity. And by mixing these cavities, you get the average gradient right. Okay, so there's it's like the chip production, or your computer chips. They throw away a certain number of them that don't perform as well. And so the same is with the cavities. Okay. To get the Q high, you actually do all sorts of things. First is you check the niobium that you use for building them. That was the big breakthrough for the Tesla cavities 30 years ago, that you just check them if there is like a rough spot or something, and then you don't use them. Then you electropolish, so you actually put some nice acid that, okay, you don't really want to know about, into the cavity, and so you remove the surface layer to make it smoother and to get rid of impurities. You rinse it at high pressure with water, so you also make it clean. You bake it out, so you heat it up, and then all sorts of stuff that is inside of the bulk material, because the surface is evaporated, and by that you improve it. But it's always a bit like black magic. You have to measure it. I mean, you test it, and you see, oh, this works. And there was like a few years ago, which still exists, sort of a fun thing that nitrogen infusion was helping. So initially it was meant to be used at high temperature to improve the gradient, but then it turned out that if you did that very slowly, then actually the cavity became better. And at that time, nobody, I mean, everybody was, oh, nice result. We don't exactly know why, but we see that's the case. And so here you see like how such a treatment, in this case, nitrogen infusion, can improve the Q of a cavity like that. Okay, so this is black magic. That's why without the experiments, RF, you cannot be sure about it. Just to show you the extreme other case, which is the click accelerating structure. This is 12 gigahertz. So this is actually this long. The other one was a meter long. This is this long. Has 12 gigahertz, 23 centimeter. There it is, 100 megavolts per meter. And it's normal conducting, and it's traveling wave. So that's the extreme other. We don't have traveling wave in our case. But just to show you, such a cavity, you put the power into one side, then it goes through the cavity. For traveling wave, you tend to speak about structure and not cavity. And in the other case, cavity, that's just like, but it's the same thing. And then on the other side, you take it out again. So you let it just pass. And then you have damping features for beam stability that are not important at this moment. And so what happens here is, because it's it's normal conducting, it's not a good conductor, you lose power as you go through. So the power is, I mean, the energy that is flowing here is being reduced as you go through it. And then if you have the beam, it takes out even more power. And so what you have to make sure in the design is that you have to leak, I mean, you want only a small fraction of the power to leak out, like a third or so, a third being lost in the walls and a third maybe going to the beam. And then you can play with the length to get more energy into the beam, but also you get less at the end, and it means also that the gradient is less at the end. Okay, so that's the other thing. This here is much simpler because you don't need this device which can deal with reflected power. But obviously for a superconducting cavity, since there is no decay, you would have to make the cavity really long to make it useful. Okay, and here you surf the wave. I think an RF person is going to kill me for this type of simplicity, but okay, so you just go with it, and you don't have this backwards reflected one. Now, this is also limited in gradient, but here the most important one is the breakdown, which you also have for superconducting cavities, but there it tends to be now less relevant. And that just means you fill your cavity with energy, you even have your beam going through, and then suddenly it says bang, and you have a short. You have like a spark from one wall of the cavity to the other, which shortens the cavity. The field collapses because all of the energy is put into the spark. And you see here what it does to the beam. This is the beam, a pulse where during the pulse there was a breakdown, and you had a nice beam before, and then suddenly after the breakdown, the beam was at a different location, the rest of the beam, just because it was short, and it's really fast. It's like nanoseconds. Okay, and actually this happens, it's not like the cavity has one value, but the value is sort of has a likelihood to break down. And that likelihood depends on the field. And so what you do is you have to make the likelihood small, and you have to actually push the cavities to that. So you have to train them first. You get more sparks at the beginning, and then by training them, you get less and less. And so it takes quite some time. And then you have a certain breakdown probability. And you make that small enough that, like in click, only in 1% of the pulses, a single cavity breaks down. Okay. So, but this is, again, black magic. And you do all sorts of things with material and surface treatments and very precise surface. Okay, good. So these are the extremes. Now I said we just have standing wave. That's much easier. So now coming to the impedance, I was asked to especially explain the shunt impedance. I don't know. So the impedance, as you would see it in a modern way, is there's energy stored in the cavity, which depends on the voltage across the cavity, so it's the length times the gradient squared. Squared is obvious. The energy in a sort of a vacuum in an electric field is proportional to the electric field squared, like the magnetic field squared. So everything will depend on the square of your voltage. However, how does it depend on that? There's a proportionality factor, and that's called R over Q. This is the impedance times omega times the frequency in radians of your RF. So the stored energy depends on the voltage squared, this R over Q, which is a funny unit. The R frequency, we'll see that, and the this here contains the shape. And now a high R over Q also means that unwanted fields are very important. But let's forget it for a second. And typically, a cavity that has a smaller hole for the beam has a higher R over Q than one that has a larger one. Okay, that's for the RF experts to design. I should warn you, there are two types of ohms for the R over Q, Linac and circuit ohms. And you can get really confused. They're different by a factor 2, so you cannot tell from the unit what it is. And that is, the people doing rings typically think about the current being a sine-like current. So, and people in the Linac, they think about the current being points that come, sort of delta functions, a sequence of delta functions come with the. So that makes a factor 2 difference for the impedance you get. And ring people add a factor F that describes the bunchedness of the beam. So if the beam is delta functions, this factor F is 2. If the beam is a nice sine-like charge distribution, then this is 1. But it's very confusing. And sometimes you look at the table and it says so and so many ohms. You say, do I need to multiply by 2 or not? Okay. Now, what is the power lost in the structure? And so the power lost in the structure is the energy inside of the structure divided by Q times omega, the frequency of the structure. That is, Q is defined as the stored energy divided by the ohmic loss in the cavity per RF radiant cycle. That's just a definition. Okay, so that's why Q is the stored energy divided by the loss over one cycle. So the loss divided by omega is the energy lost in one cycle. So this divided by the omega, by the energy loss per cycle, that's Q. Okay, and so you find that the loss is proportional to the voltage squared divided by R over Q times 1 over Q. So the Q actually disappears in there. Okay. This is really traditional. So that's actually the explanation I will show for why this is called R over Q. So just to give you a feel, a superconducting cavity typically has 10 to the 10 Q, maybe 2 10 to the 10, it depends on. And a normal conducting cavity 10 to the 4. And for a normal conducting cavity, it depends actually on the frequency because the skin depth matters. And so a higher frequency has a lower Q in a normal conducting cavity, okay? So now why shunt impedance? Why was that R? And we have the P loss. So in the good old days, people thought they take the effective voltage divided by the ohmic power loss, which is the gradient times the length divided by the loss, and they call that R. And this mixes material properties together with geometry. And actually the way to separate that is, so that makes the simple thing. And the way to separate that is you say, but in reality, the stored energy depends on the R over Q, which should have had its own name initially. And then you have the Q, which is material dependent and also a little bit geometry dependent. It's not totally independent of the geometry, but because the shape matters, okay? So that's why this is this weird thing and why people always talk about the R over Q instead of just R or something. It's like with these angles and offsets instead of transverse momentum and offset, okay? Good. Now let's have a quick look. What is the RF to beam efficiency? That's basically the energy taken by one beam pulse divided by the energy you put in to the RF pulse, sending it down. Okay, that's trivial. And now you can, in a simple model, you can assume that the RF pulse is mostly, in many applications, just a constant power for some time. That's called tau RF. And the beam pulse is shorter in time because you need to fill the cavity first before you actually send beam into it. And so the tau of the beam, you have to divide by the tau of the RF. That's the first inefficiency factor that you get. I'll show the example for IRC later. And then you also take, during the beam pulse, you take so and so much power into the beam, which you have to divide by the power of the RF that you put in during that time. I think that's fairly straightforward. So you have two factors. And then now you can spell that out. And in a simple, so for an RF person, this is simplified way. What you do is you have the time of the beam, and typically you divide it by the time of the beam times the time it takes to fill the cavity. You don't have an RF pulse that's longer than that for good reasons. And you take the power into the beam, which is obviously the power, I mean, the RF power here has to provide the power into the beam, the power that you lose in the walls, plus the power, for example, in a traveling wave structure that leaks out, or in a accelerating, in a standing wave cavity, what is reflected, okay? Quick example for linear colliders, they are masters of RF. So the R over Q of a IRC cavity is 1.036 kilo ohm per meter. The one of click is 11 kilo ohms per meter. So that's why there's a much higher frequency. The Q, 6,000, 10 to the 10-ish. Actually, now they aim for 210 to the 10. And so you see the R prime here is less than 100 mega ohms per meter, and this here is 10 to the 7 mega ohms per meter. Okay, so that's why superconducting cavities are great. So the amount of power you lose into the wall compared to the power you put into the beam, it's 1 over 650. So you use, or you almost have 2,000 times more power you give to the beam than to the walls. While in click, this is 0.8. So it's about the same power lost in the copper as into the beam. This is just here showing the overall efficiency. So for the IRC at the time, sorry, it was 730 microsecond beam pulse and 900 microsecond fill time, so roughly 50%. And then for click, you see here the beam pulse, the fill time was shorter than the beam pulse, but you had only 27 megawatts into the beam and roughly the same in the wall and something small leaking out at the end. So 27%. In the superconducting cavity, the next thing is you have to, this little power you give into the wall, you have to cool away. And then because you lose this power at very low temperatures, you pay for the Carnot inefficiency of cooling. So typically you aim for a watt per meter loss. And then the Carnot inefficiency tells you that to cool that with a system that operates at room temperature on the other side, you have to spend something like, I mean, that's 300K. The other one is 2K, so 150 times more power, electric power into your cooling system than you extract at 2K. And then technical, I mean, the system is a technical system, so it's 25% efficient. So you need roughly 700 times more electric power to remove the 1 watt, so 700 watts per meter for the cooling system. Okay, so that becomes relatively important compared to other systems. So like in IC, there was 1.6 kilowatt RF power per meter roughly, and about 0.7 kilowatts per meter for the cooling. So you have to take that into account. That's a drawback of superconducting cavities. So what do you have now as choices? Generally, in a superconductor, you have little loss in the wall, so you can afford to extract the power slowly. You also don't need to fill the cavity with power, I mean, with high power. You can take time. So the peak power of your klystrons can be reduced enormously. You just give a longer pulse. That's great. But we need cryogenics, and you have to have a standing wave cavity. There are designs also where people think about traveling wave, but typically it's standing wave because you need to keep the energy in the cavity for long. Normal conducting, you can use traveling or standing wave. For click, for Linux, typically it's traveling wave because it's cheaper, easier, and you have a very high beam current to extract energy, but it can also be standing wave. If it's traveling wave, actually you can taper the structure also to compensate for the energy reduction along the structure. So you make it more, sort of give it a smaller aperture at the end, so you get more field out of that. For the muon collider, we have only standing wave in normal conducting, superconducting versions. So a quick example, the RCS1. So here you see we accelerate one beam going around one way, the other beam going around the other way, and we have the RF stations distributed all over. The bunches are very short compared to the wavelengths of the RF. So we get high frequency content in the beam. This is basically our F is approaching 2. That's what it says. We have very short bunches. So you see, the longer your bunch, the less high frequencies you excite. But that's just a sign. Now let's see. We have the IC cavities. So we have also a length of the structure of about 104 centimeters. A voltage in this design of 30.6 megavolt per. That's the integrated voltage, so not per meter. The impedance was 1036 ohm. So we can calculate with that, just using the formula that I showed before, the stored energy in the cavity. It's 110 joule. Well, okay. Now let's look at the charge per bunch, 210 to the 7, 2 point, sorry, I'm a bit tired obviously, 2.7, 10 to the 12. We operate at 45 degrees or 135, I mean, it doesn't matter. Square root of 2 of the voltage is there for acceleration, square root of 2 is there for bucket forming. So we have roughly 0.7 times 30 megavolt acceleration. Then we multiply the charge with the field, and we find that we extract something like 9.3 joule. So we extract, I mean, 9 joule out of 110, almost 10%. So obviously there is an important impact on that. In a LINAC, typically you extract like 1% or less. I mean, you extract a very small amount, and you compensate that by having a train of bunches where each bunch takes out a little bit, and so in between you fill it back in. And you can also do the calculation, I showed at the end, about the change of gradient, which you get from treating this as a wake field. With the R over Q, you can calculate the change of gradient for the fundamental mode, and it's almost 2 megavolts. So it's substantial. This here corresponds to 20, so it's an almost 10% change of gradient, okay? So how does that look like for the cavity? And here you see the voltage in the cavity and the number of turns. So this is just one turn. So what you have, and here it's the phase. So you start, and sorry, it's 2 cases. Like we have the one where the 2 bunches come with a large distance. So here you have with the this red one, you have the one bunch coming, and then the bunch that goes the other way comes half a cycle, I mean half a turn later. And you have the case where they just happen to almost meet in the cavity. So one comes and the other one comes right away, and then they go around the circle again. And so what you see here is that the voltage in the cavity really changes in a strong way. So this is the voltage before, then it's reduced substantially by extracting the energy, and then it's recovered with the RF, and then it comes back. And the same with the phase, because the bunch takes out, I mean, you have your voltage, your RF, looks like that, and your bunch arrives at such a moment, so it produces a negative voltage like this, which is cosine-like with respect to here. So that reduces the amplitude, but it also reduces the phase of this oscillation. Okay, good. So that's what we see. Quick remark, that's why we like to play with RF frequencies. So think the wavelength, which is the inverse of the frequency. What happens if you change the frequency, the wavelength? So we said the R over Q is given by the voltage divided by the energy stored. It should be U, but I copy pasted, sorry, from some different lecture than the other one times omega. And now the energy in the structure, if you keep the geometry the same and just blow it up, keep the voltage the same, goes with the volume. Trivia, with a third power. Okay, so the energy is proportional to the volume. The energy gain of the particle is proportional to the length. Same, I mean, okay. And the frequency goes as 1 over lambda. Now you put all of that together and you find that the R over Q is actually a constant. So the impedance of a cell does not depend on the size of the cell. It's always the same. It's actually totally convenient. I mean, you can do lots of things and annoy RF experts by making simple predictions. And for a typical superconducting cavity, this is 110 ohms per cell in many cases, because that's a very efficient one. But it also means that if you now take a lower frequency, a larger lambda, what you take out is proportional to the length times the gradient, but the energy stored goes with the third power. So actually, you take out a much smaller fraction, because what you can think of is just you transversely the stored energy. I mean, it becomes larger because the transverse cross-section is getting much larger. So it goes, the stored energy goes up, compared to what you extract, goes up with the square. In the cell, it goes up with the volume, but then you lose longitudinally because also the particle extracts more, and so you're left with the square. So that means, indeed, going to a lower frequency, you extract less of the stored energy. Okay. Just to give you some quick numbers on the power drivers. So this here was what I showed on Monday, and for the RCS. And just here you see this was the volt plug of the RF. So this is the peak power. Then we have pulsed operations. So we the 900 megawatts of peak power become like 3 megawatts, because we operate only a fraction of the time, like a 30%. Then you need your systems to produce the RF from the volt plug are having some inefficiency, typically of the order of a factor 2 or a bit less. So you see you need roughly 50% more power to produce the RF power. That's where you are. And that works for all of the systems. And then here, as I said, the cryogenics is important. And you see that here the total cryogenics is like 20. And this here is a bit more than 40. And so indeed, the cryogenics is a good fraction of the overall power that you need for the RF. Okay. Good. With that said, let's quickly go through the RF systems for the cooling. So there's a list. I mean, it's lower frequencies, and they need to be normal conducting because they operate in a high magnetic field. And the superconductor doesn't like that. I mean, it's really that the superconductor stops being superconductor in a high field. So you're limited for that. I will not go through all the calculations because that's tough. Now, there's a specific problem. I talked about the breakdown quickly before, and in a strong magnetic field, the breakdown becomes worse. And so what happens in a breakdown in a normal cavity, if it's just sitting somewhere with RF, is that you have an emitter. So you have one side that decides to emit electrons. And actually, these sides can dynamically form. There are simulations like from Tampere University, how that does. And then they go out, and they follow sort of the field lines, the electric field lines and magnetic field lines, and they spread over the cavity. And annoy the cavity, and that can lead to an avalanche effect. Okay. Now, what happens if you have a magnetic field? Then, say a longitudinal magnetic field, then these electrons will spiral around the field. It's like in a detector. They are very low in energy, so they go, and so they will all happily go together and hit one spot on the other side. And then everything that's produced there will happily go backwards and hit the first spot again. And so it goes back and forth. And you can imagine that this is way worse than sort of giving everybody a little hit. Okay, that's the problem. And then depending on the magnetic field, this becomes better or worse. Here's a nice animation from our CAA colleagues for that. You see this here is the free cavity. And particles indeed sort of are scattered. They move all around. And this is the cavity in a magnetic field. And you really hit one spot. And now that will lead to a breakdown, because if the spot becomes too hot, you can destroy it, and then you get your spark. So what to do about that? There were two solutions. There were one that is actually, this here, by the way, is the cavity that was meant to be used for mice. So one is to use a material that is less sensitive to being hit. And beryllium is good for two reasons. It can sort of take a larger power, and also it is thinner in a way, I mean, than copper. So actually, your electrons will dispose the energy over a larger volume. So using beryllium instead of copper is going to improve the situation. That has been tried. Results. And the other one is using a gas-filled cavity with high pressure and hydrogen. So the first one here, okay, so we well, the other thing is we could also make much shorter pulses because then the heating is for a shorter time, so it's fine. You just fill the cavity more rapidly because there's a single bunch taking out the energy, so if you fill it twice as quick, the pulse is half as long. But then you have to pay for twice the peak power, and then I mean, we talk about like something in the half billion range or whatever. So you don't want that. So now experimentally it has been tested in muon that actually you can put beryllium at the end plates, and there the test was limited to 3 Tesla, and 50 megavolts per meter have been achieved with 30 microsecond RF pulse. Here you see some of the temperature rises measured in copper, aluminum, and beryllium. You see, as I said, beryllium is better than copper, and then it also can sustain higher heat loads, as you can see there. And so this year, with the beryllium cavities, were actually, funny enough, the one with magnetic field was achieving a higher field limit than the one without. Okay, and you see, like for copper, there's a reduction. There's already a lower limit initially, and then it's further reduced. And yeah, okay, so that's what it is. Okay, so that's the approach we are mostly following. The other one is you fill high pressure hydrogen, like 100 bar or so, into your cavity. What does that do? The electron is coming from the surface, then it's accelerated by the longitudinal field, and it hits a hydrogen atom. So what molecule. So what it does do is it gives some of its energy to the molecule, and then it's slow, and then basically it gets stuck. And what you have to make sure is that the rate of collision is such that your electron cannot acquire enough energy before it hits, on average, a molecule to ionize the molecule. Because if it would be able to do that, it would actually create an avalanche. Okay, so the pressure, therefore, has to be fine. This here is from Tolstrops. I didn't find a better plot, so this is really based from an old one. So here you see the density of hydrogen, you see the gradient that could be attained, and you see it's a linear dependence, exactly because the likelihood, I mean, the mean free path depends linearly on the density. And then there is, at some point, in 65 megawatts per meter, you're limited because you get surface effects, and that you cannot cure in the volume. Really neat, but certainly that would change the design because you have also the muon see the hydrogen, and so you would get cooling and multiple scattering already in the cavity. Okay, very nice. Then there's effort on the klystrons. So again, the klystrons are expensive, especially if you have normal conducting RF, because the peak power matters. And we profit there enormously from the ones that have been done for click at 1 gigahertz, because click uses that for the drive beam, and then the ones for the IC, which are at 1.3 gigahertz. And for click, actually, these are efficiencies that you typically get from the klystron, so 75, 65%. And we have a design approach starting from click, now also being considered for other projects, that is even more efficient than that, which one of our click people has started doing. And so with the 700 megahertz klystron, or the ones we expect similar performances. There's an additional inefficiency from the modulator, but what you have to do is first you take the energy from the grid, you store it locally, and then you feed the klystron for the short pulse. But this is an additional, maybe here, 10% loss compared to that. Okay. This is, by the way, how a klystron works, for those of you curious. It's very simple. You have a current that you accelerate here with a high voltage, and then when the current, so it would normally just flow to here, DC current. And what you do is you have a little bunch of cavities, so you put a little modulation on the energy of these electrons. And then they have time, and because they have a little different energy, they start sort of debunching, because some are a little faster, some are a little slower. So you get actually a modulation where you suddenly you see sort of the current change in time. So you have denser and less dense spots. And then you have another cavity which extracts the energy from the beam, like what we saw in the normal cavity, and then send this as RF to your accelerator or whatnot, and you collect the rest here. And so that's why there's an inefficiency, because you certainly don't get 100% of the power that you put into this beam extracted here, but you get like 70% or more. So that's quite impressive. Okay, so it's like a little accelerator. Very quick to test these high field normal conducting cavities, we plan to do tests. So this is the one that's SLAC. SLAC seems to run faster than everybody else. We have attempts to do this at INFN, at the UK, and SLAC came late and said, we want to do it, and they will be ready, I think, before everybody else. This would be done at 3 gigahertz, well, 2.856, which is the US 3 gigahertz. But being able to test in a magnetic field cryogenics, just some equipment, and you see then there's more. Okay, and then we try also to have a test stand at INFN and in the UK. And that would be great because we need to do many tests, because as you saw, that there is like a small breakdown rate probability, and you have to test therefore a cavity for a long time to see this small rate. Okay, so that was there. Now in the reserve, very quickly, filling a cavity is not trivial. It takes longer than you would imagine from the energy that you have. So I show that here. It's just, you see the formula in the backup, including a calculation why it is like that, which is hand waving to show that. But just to say, it's not just power times time, the energy that you manage to put into the cavity. The wake field, because there was the question on Monday or so, if you can see that as extracting energy from the cavity or leaving a field. And so this leaving a field model, if you go through this slide, actually is the same as extracting energy, and it just shows that the two give the same result. And the electric field that you leave is proportional to R over Q times omega times the charge divided by 2. Okay, you can do that offline. And then just to show you how important the peak power is, a quick reminder of the click concept. So for click, you would need something like 100,000 klystrons at 3 TeV to power that, and that's really expensive. So for click, the selling point was to actually not have klystrons for the main beam, but rather produce a very long beam pulse with klystrons here, then compress that and use this beam pulse to power your main linac. And by that, you become very cost efficient. But I mean, it's like a huge big klystron, and all of this effort just because the klystrons themselves are so expensive. This is how that works. You have a drive beam, and like in a klystron, 100 amp low energy beam, which you use here. You decelerate. This is actually an animation from SLAC. You decelerate it. By that, you build up power, which you then send into the accelerating structures. This computer is much slower than and then you feed that power in here to accelerate a low current main beam, but with a high field. Okay, it's like a giant transformer, and it's like a huge big klystron. This is how it looks like in practice. So it's on these drawings, it's always simple. This is the concept here. You start with 104 microseconds, and then you compress it to 250 nanosecond pulses, which you feed in the different sectors. And this is an... Does that not work? Okay, this animation doesn't work. It does not work. Okay. Okay, so sorry, this shows with lemmings how that works, and this has been tested. But it shows that, yeah, a whole concept for a linear collider was based on avoiding these high power klystrons, and that's a real driver for them. Okay, that was RF. Shit. Okay.
Any quick question for the immediate? Otherwise, we have, not today, but tomorrow, another question slot. Or we move to Kevin. Thank you, Daniel. Oh, you got one? Just a moment.
You were pleasantly surprised that the ILC cavities were possibly applicable from muon collider. What was the sort of determining factor to seeing if that was the case?
Okay, so I was worried about the fact, I mean, doing the simple calculation, you see that, okay, we extract 10% of the stored energy. We want to have a 1 per mil energy spread at the end. it's easy to imagine that you improve what you get by all of these tricks by factor 10. So we are missing something. And then what really was the saving grace is that well, one is you have the I mean, you can compensate in part the different acceleration by having some of the RF. I mean, in this trick here, what happens is that a particle that comes late sees a already reduced field, but on the other hand, and sees something that normally was bigger. So that compensates. And if you have enough longitudinal motion, then it also means that the particle is seeing too little and too much turn by turn, and that changes, and that averages out. And so doing the full simulation actually showed that it averaged out better than I had expected, to be honest. And that was that. So I had, but that's really detailed simulations of the RF experts. There you have to rely on them that showed that it was possible. Yep.
Okay, thank you, Daniel, once more.